Test. Okay, it works. Okay, good. We should get started soon. So today we'll be talking about recurrent neural networks, which is one of my favorite topics, one of my favorite models to play with and put into neural networks just everywhere. They're a lot of fun to play with. In terms of administrative items, recall that your midterm is on Wednesday. This Wednesday, you can tell that I'm really excited. I don't know if you guys are excited. You don't look very excited to me, but assignment 3 will be out due this Wednesday. It will be out in Wednesday. It's due 2 weeks from now on Monday, but I think since we're shifting it, to Wednesday, we planned to have released it today, but we're going to be shifting it to roughly Wednesday, so we'll probably defer the deadline for it by a few days. And assignment 2, if I'm not mistaken, was due on Friday, so if you're using 3 late days, then you'd be handing it in today. Hopefully not too many of you are doing that. Are people done with assignment 2, or how many people are done? Okay, most of you. Okay, good. Great. Okay, so we're doing well. So currently in the class, we're talking about convolutional neural networks. Last class specifically, we looked at visualizing and understanding convolutional neural networks. So we looked at a whole bunch of pretty pictures and videos, and we had a lot of fun trying to interpret exactly what these convolutional networks are doing, what they're learning, how they're working, and so on. And so we debugged this through several ways that you maybe can recall from last lecture. Actually, over the weekend, I stumbled by some other visualizations that are new. I found these on Twitter, and they look really cool. And I'm not sure how people made these, because there's not too much description to it. But it looks really cool. This is turtles and tarantula. And then this is chain and some kind of a dog. And so the way you do this, I think it's something like Deep Dream. It's, again, optimization into images, but they're using a different regularizer on the image. So in this case, I think they're using a bilateral filter, which is this kind of a fancy filter. So if you put that regularization on the image, then my impression is that these are the kinds of visualizations that you achieve instead. So that looks pretty cool, but I'm not sure exactly what's going on. I guess we'll find out soon. OK. So today we're going to be talking about recurrent neural networks. What's nice about recurrent neural networks is that they offer a lot of flexibility in how you wire up your neural network architectures. So normally when you're working with neural nets, here in the case on the very left here, where you're given a fixed-sized input vector, here in red, then you process it with some hidden layers in green, and then you produce a fixed-sized output vector in blue. So say an image comes in, which is a fixed-sized image, and we're producing a fixed-sized vector, which is the class scores. With the recurrent neural networks, we can actually operate over sequences. Sequences at the input, output, or both at the same time. So for example, in the case of image captioning, and we'll see some of it today, you're given a fixed-sized image, and then through a recurrent neural network, we're going to produce a sequence of words that describe the content of that image. So that's going to be a sentence that is the caption for that image. In the case of sentiment classification in NLP, for example, we're consuming a number of words in sequence, and then we're trying to classify whether the sentiment of that sentence is positive or negative. In the case of machine translation, we can have a recurrent neural network that takes a number of words in, say, English, and then it's asked to produce a number of words in French, for example, as a translation. So we'd feed this into a recurrent neural network in what we call sequence-to-sequence kind of setup. And so this recurrent network would just perform translation on arbitrary sentences in English into French. And in the last case, for example, we have video classification, where you might want to imagine classifying every single frame of a video with some number of classes. But crucially, you don't want the prediction to be only a function of the current time step, the current frame of the video, but also all the frames that have come before it in the video. And so recurrent neural networks allow you to wire up an architecture where the prediction at every single time step is a function of all the frames that have come in up to that point. Now, even if you don't have sequences at input or output, you can still use recurrent neural networks, even in the case on the very left, because you can process your fixed-sized inputs or outputs sequentially. So for example, one of my favorite examples of this is from a paper from DeepMind from a while ago, where they were trying to transcribe house numbers. And instead of just having this big image feed into a COMNET and try to classify exactly what house numbers are in there, they came up with a recurrent neural network policy where there's a small COMNET, and it's steered around the image spatially with a recurrent neural network. And so the recurrent network learned to basically read out house numbers from left to right sequentially. And so we have fixed-sized input, but we're processing it sequentially. Conversely, we can think about, this is also a well-known paper called DRAW. This is a generative model. So what you're seeing here are samples from the model where it's coming up with these digit samples. But crucially, we're not just predicting these digits at a single time, but we have a recurrent neural network, and we think of the output as a canvas, and the recurrent neural network goes in and it paints it over time. And so you're giving yourself more chance to actually do some computation before you actually produce your output. So it's a more powerful kind of form of processing data. Was there a question over there?
Yeah. 2 slides back, I didn't really understand what it meant to have 2 arrows going out. Does it mean that it's like going back into the previous block as input, or?
Yeah, so every one of these arrows is kind of like a dependency in terms of, I guess we'll see specifics of exactly what this means. For now, arrows just indicate functional dependence. So things, so things are a function of things before, and we'll go into exactly what that looks like in a bit. Okay, so.
So what this picture draws? No, the dialect.
Oh, this one?
Yeah. What is showing here?
Oh, so these are generated house numbers. So the network looked at a lot of house numbers, and it came up with a way of painting them. And so these are not in the training data. These are made-up house numbers from the model. None of these are actually in the training set.
So these are like made up?
These are made up, yeah. They look quite real, but they're actually made up from the model. So a recurrent neural network is basically this thing, here a box in green, and it has a state, and it basically receives, through time, it receives input vectors. So at every single time step, we can feed in an input vector into the RNN, and it has some state internally, and then it can modify that state as a function of what it receives at every single time step. And so there will, of course, be weights inside the RNN, and so when we tune those weights, the RNN will have different behavior in terms of how its state evolves as it receives these inputs. Now, usually, we can also be interested in producing an output based on the RNN's state. So we can produce these vectors on top of the RNN. So you'll see me show pictures like this, but I just like to note that the RNN is really just the block in the middle, where it has a state and it can receive vectors over time, and then we can base some prediction on top of its state in some applications. Okay. So concretely, the way this will look like is the RNN has some kind of a state, which here I'm denoting as a vector h. But this can be also a collection of vectors, or just a more general state. And we're going to base it as a function of the previous hidden state at previous iteration time t-1 and the current input vector xt. And this is going to be done through a function, which I'll call a recurrence function, f. And that function will have parameters w. And so as we change those w's, we're going to see that the RNN will have different behaviors. And then, of course, we want some specific behavior out of the RNN. So we're going to be training those weights on data. So you'll see examples of that soon. For now, I'd like you to note that the same function is used at every single time step. We have a fixed function f of weights w, and we apply that single function at every single time step. And that allows us to use the recurrent neural network on sequences without having to commit to the size of the sequence, because we apply the exact same function at every single time step, no matter how long the input or output sequences are. So in a specific case of a recurrent neural network, a vanilla recurrent neural network, the simplest way you can set this up, and the simplest recurrence you can use, is what I'll refer to as a vanilla RNN. In this case, the state of a recurrent neural network is just a single hidden state h. And then we have a recurrence formula that basically tells you how you should update your hidden state h as a function of the previous hidden state and the current input xt. And in particular, in the simplest case, we're going to have these weight matrices, WHH and WXH. And they're going to basically project both the hidden state from the previous time step and the current input. And then those are going to add, and then we squish them with a tanh. And that's how we update the hidden state at time t. So this recurrence is telling you how h will change as a function of its history, and also the current input at this time step. And then we can base predictions on top of h, for example, using just another matrix projection on top of the hidden state. So this is the simplest concrete case in which you can wire up a neural network. Okay? So just to give you an example of how this will work, so right now I've just talked about x, h, and y in abstract forms in terms of vectors. We can actually endow these vectors with semantics. And so one of the ways in which we can use a recurrent neural network is in the case of character-level language models. And this is one of my favorite ways of explaining RNNs because it's intuitive and fun to look at. So in this case, we have character-level language models using RNNs. And the way this will work is we will feed a sequence of characters into the recurrent neural network. And at every single time step, we'll ask the recurrent neural network to predict the next character in the sequence. So we'll predict an entire distribution for what it thinks should come next in the sequence that it has seen so far. So suppose that in this very simple example, we have the training sequence hello. And so we have a vocabulary of 4 characters that are in this data set, H, E, L, and O. And we're going to try to get a recurrent neural network to learn to predict the next character in a sequence on this training data. And so the way this will work is we'll feed in every one of these characters one at a time into a recurrent neural network. So you'll see me feed in h at the first time step, and here the x-axis is the time. So we'll feed in h, then we'll feed in e, l, and l. And here I'm encoding characters using what we call a one-hot representation, where we just turn on the bit that corresponds to that character's order in the vocabulary. Then we're going to use the recurrence formula that I've shown you, where at every single time step, suppose we start off with h as all 0, and then we apply this recurrence to compute the hidden state vector at every single time step using this fixed recurrence formula. So suppose here we have only 3 numbers in the hidden state. We're going to end up with a 3-dimensional representation that basically, at any point in time, summarizes all the characters that have come until then. And so we've applied this recurrence at every single time step, and now we're going to predict at every single time step what should be the next character in the sequence. So for example, since we have 4 characters in this vocabulary, we're going to predict 4 numbers at every single time step. So for example, in the very first time step, we fed in the letter h, and the RNN, with its current setting of weights, computed these unnormalized log probabilities here for what it thinks should come next. So it thinks that h is 1.0 likely to come next. It thinks that e is 2.2 likely, l is -3 likely, and o is 4.1 likely right now in terms of unnormalized log probabilities. Of course, we know that in this training sequence, we know that E should follow H. So in fact, this 2.2, which I'm showing in green, is the correct answer in this case. And so we want that to be high, and we want all these other numbers to be low. And so in every single time step, we have basically a target for what next character should come in the sequence. And so we just want all those numbers to be high and all the other numbers to be low. And so that's, of course, encoded in the gradient signal of the loss function. And then that gets backpropagated through these connections. So another way to think about it is that at every single time step, we basically have a softmax classifier. So every one of these is a softmax classifier over the next character. And at every single point, we know what the next character should be. And so we just get all those losses flowing down from the top, and they will all flow through this graph backwards through all the arrows. We're going to get gradients on all the weight matrices. And then we'll know how to shift the matrices so that the correct probabilities are coming out of the RNN. So we'd be shaping those weights so that the correct behavior, the RNN has the correct behavior as you're feeding characters. And so you can imagine how we can train this over data. Are there any questions about this diagram? Go ahead.
The WXH and WXY are the same for every arrow, or they depend on?
Yeah, thank you. So at every single time step, we're applying, as I mentioned, the same recurrence, the same functions always. So we have a single WXH at every time step, we have a single WHY at every time step, and the same WHH applied at every time step here. So we've used WXH, WHY, WHH 4 times in this diagram. And in backpropagation, when we backpropagate through, you'd of course have to account for that, because we'll have all these gradients adding up to the same weight matrix because it has been used at multiple time steps. And this is what allows us to process variably sized inputs, because at every time step we're doing the same thing, so not a function of the absolute amount of things in your input. Okay, question?
What are common schemes for initializing the first H0?
What are common things for initializing the first H0? I think setting it to zeros is quite common. Set H in the beginning to 0. Good?
Doesn't the order that you see the data set matter to you?
Does the order in which we receive the data set matter? Yes, because, so are you asking if I plugged in these characters at a different order?
No, I'm talking about words in different order. So if you see hello first or some other word.
Yeah. So if this was a longer sequence, the order in this case always does matter, because at every single point in time, if you think about it functionally, like this hidden state vector at this time step is a function of everything that has come before it, right? And so this order just matters for as long as you're feeding it in. We're going to go through some specific examples, which I think will clarify some of these points. Okay, so let's look at a specific example. In fact, if you want to train a character level language model, it's quite short. So I wrote a gist that you can find on GitHub, where this is 100-line implementation in NumPy for a character level RNN that you can go through. I'd actually like to step through this with you so you can see concretely how we could train a recurrent neural network in practice. And so I'm going to step through this code with you now. So we're going to go through all the blocks. In the beginning, as you'll see, the only dependence here is NumPy. We're loading in some text data. So our input here is just a large sequence of characters, in this case, a text input.txt file. And then we get all the characters in that file, and we find all the unique characters in that file, and then we create these mapping dictionaries that map from characters to indices and from indices to characters. So we basically order our characters. So say we've read in a whole bunch of file and a whole bunch of data, and we have 100 characters or something like that, and we've ordered them in a sequence. So we associate indices to every character. Then here we're going to do some initializations. First, our hidden size is a hyperparameter, as you'll see with recurrent neural networks. So here I'm choosing it to be 100. Here we have a learning rate. Sequence length here is set to 25. This is a parameter that you'll become aware of with RNNs. Basically, the problem is if our input data is way too large, say like millions of time steps, there's no way you can put an RNN on top of all of it because you need to maintain all of this stuff in memory so that you can do backpropagation. So in fact, we won't be able to keep all of it in memory and do backprop through all of it. So we'll go in chunks through our input data. In this case, we're going through chunks of 25 at a time. So as you'll see in a bit, we have this entire data set, but we'll be going in chunks of 25 characters at a time. And at every time, we're just going to backpropagate through 25 characters at a time because we can't afford to do backpropagation for longer because we'd have to remember all that stuff. And so we're going in chunks here of 25. And then we have all these W matrices that here I'm initializing randomly and some biases. So WXH, HH, and HY. And those are all of our parameters that we're going to train with backprop. OK? Now I'm going to skip over the loss function here, and I'm going to skip to the bottom of the script. Here we have a main loop, and I'm going to go through some of this main loop now. So there are some initializations here of various things to 0 in the beginning, and then we're looping forever. What we're doing here is I'm sampling a batch of data. So here is where I actually take a batch of 25 characters out of this data set. So that's in the list inputs. And the list inputs basically just has 25 integers corresponding to the characters. The targets, as you'll see, is just all the same characters, but offset by 1, because those are the indices that we're trying to predict at every single time step. So the inputs and targets are just lists of 25 characters. Targets is offset by 1 into the future. So that's where we sample basically a batch of data. Here, this is some sampling code. So at every single point in time, as we're training this RNN, we can, of course, try to generate some samples of what it currently thinks characters should actually, what these sequences look like. So the way we use character-level RNNs in test time is that we're going to seed it with some characters, and then this RNN basically always gives us a distribution of the next character in a sequence. So you can imagine sampling from it, and then you feed in the next character again, and you sample from the distribution, and you keep feeding it in. So you keep feeding all the samples into the RNN, and you can just generate arbitrary text data. So that's what this code will do, and it calls the sample function, so we'll go into that in a bit. Then here, I'm calling the loss function. The loss function receives the inputs, the targets, and it receives also this hprev. Hprev is short for hidden state vector from the previous chunk. So we're going in batches of 25, and we are keeping track of what is the hidden state vector at the end of your 25 letters, so that we can, when we feed in the next batch, we can feed that in as the initial h at that time step. So we're making sure that the hidden states are basically correctly propagated from batch to batch through that hprev variable, but we're only backpropagating those 25 time steps. So we feed that into loss function, and we get the loss and the gradients on all the weight matrices and all the biases. And here I'm just printing the loss. And then here's a parameter update, where the loss function told us all the gradients. And here we are actually performing the update, which you should recognize as an attgrad update. So I have all these cached variables for the gradient squared, which I'm accumulating and then performing the attgrad update. Okay? So I'm going to go into the loss function and what that looks like now. The loss function is this block of code. It really consists of a forward and a backward method. So we're computing the forward pass and then the backward pass in green. So I'll go through those two steps. So in the forward pass, you should recognize basically we get those inputs, the targets. We're iterating. We receive these 25 indices, and we're now iterating through them from 1 to 25. We create this x input vector, which is just zeros, and then we set the 1-hot encoding. So whatever the index in the input is, we turn that bit on with a 1. So we're feeding in the character with a 1-hot encoding. Then here I'm computing the recurrence formula using this equation. So h is at t, here h is and all these things. I'm using dictionaries to keep track of everything at every single time step. So we compute the hidden state vector and the output vector using the recurrence formula in these two lines. And then over there, I'm computing the softmax function. So I'm normalizing this so that we get probabilities. And then your loss is negative log probability of the correct answer. So that's just a softmax classifier loss over there. So that's the forward pass. And now we're going to backpropagate through the graph. So in the backward pass, we go backwards through that sequence from 25 all the way back to 1. And maybe you'll recognize, I don't know how much detail I want to go in here, but you'll recognize that I'm backpropagating through a softmax. I'm backpropagating through the activation functions. I'm backpropagating through all of it. And I'm just adding up all the gradients and all the parameters. And one thing to note here especially is that these gradients on the weight matrices, like WHH, I'm using a plus equals because at every single time step, all of these weight matrices get a gradient, and we need to accumulate all of it into all the weight matrices because we keep using all these weight matrices at every time step. And so we just backprop into them over time. And that gives us the gradients, and then we can use that in loss function and perform the parameter update. And then here we have finally a sampling function. So here is where we try to actually get the RNN to generate new text data based on what it has seen in the training data and based on the statistics of the characters and how they follow each other in the training data. So we initialize with some random character, and then we go for until we get tired. And we compute the recurrence formula, get the probability distribution, sample from that distribution, re-encode it in one hot representation, and then we feed it in the next time step. So we keep iterating this until we actually get a bunch of text. So is there any question over just like the rough layout of how this works? Go ahead.
So when you're doing the gradient propagation, are you bringing in, so in this example, for example, would you, like I think it says ELLO at the top there, are you bringing in 4 of those 4 vectors, and like, are you treating that as the Y for that? So you have a batch of 25, for example.
That's right.
And each of those Y's would be a vector that's like you call it a one hot.
Yeah.
And so are you treating, do you do the back propagation with that, all those 25 Y's at once?
That's right, exactly. So we have basically 25 softmax classifiers at every batch, and we backprop all of those at the same time, and they'll all add up in the connections going backwards. That's right. Okay, go ahead.
So we don't use regularization here?
Do we use regularization here? You'll see that I probably do not. Yeah, I guess I skipped it here. But you can, in general, I think sometimes I tried regularization, and I don't think it's as common to use it in recurrent nets as outside. Sometimes it gave me like worse results, so sometimes I skip it. But it's kind of a hyperparameter. Go ahead.
So when you say you choose a batch of 25, is it like 25 characters that follow one another?
Yeah, that's right.
Like,
So.
Won't there maybe be like multiple words expressions?
Yeah, that's right. So in the sequence of 25 characters, here we are very low level on the character level. And we don't actually care about words. We don't know that words exist. It's just characters, indices. So this RNN, in fact, doesn't know anything about characters or language or anything like that. It's just indices and sequences of indices, and that's what we're modeling. Yeah. Go ahead.
Is there a reason that we use a constant segment size instead of like using like spaces as delimiters, for example?
Can we use spaces as delimiters or something like that instead of just constant batches of 25? I think you maybe could, but then it kind of, it's just you have to make assumptions about language. We'll see soon why you wouldn't actually want to do that, because you can plug anything into this, and we'll see that we can have a lot of fun with that. OK. So let me show you now what we can do. We can take a whole bunch of text. We don't care where it came from. It's just a sequence of characters. And we feed it into the RNN, and we can train the RNN to create text like it. And so, for example, you can take all of William Shakespeare's works. You concatenate all of it. It's just a giant sequence of characters. And you put it into the recurrent neural network, and you try to predict the next character in a sequence for William Shakespeare poems. And so when you do this, of course, in the beginning, the recurrent neural network has random parameters. So it's just producing a garble at the very end. So it's just random characters. But then when you train, the RNN will start to understand that, OK, there are actually things like spaces. There's words. It starts to experiment with quotes. And it basically learns some of the very short words like here or on and so on. And then as you train more and more, this just becomes more and more refined. And the recurrent neural network learns that when you open a quote, you should close it later. Or that the sentences end with a dot. It learns all of this stuff statistically just from the raw patterns without actually having to hand code anything. And in the end, you can sample entire infinite Shakespeare based on this on the character level. So just to give you an idea about what kind of stuff comes out, alas, I think he shall become approached, and the Dane with little strain would be attained into being never fed, and who is but a chain and subject of his death, I should not sleep. So this is the kind of stuff that you would get out of this recurrent network. Go ahead.
But this could never generate a quote longer than 25 characters long, right? Because it can't remember that it opened a quote.
Yeah, thank you. So you are bringing up a very subtle point, which I'd like to get back to in a bit. OK, so we can run this on Shakespeare, but we can run this on basically anything. So we were playing with this with Justin, I think, like roughly a year ago. And so Justin he found this book on algebraic geometry. And this is just a large LaTeX source file. And we took that LaTeX source file for this algebraic geometry and fed it into the RNN. And the RNN can learn to basically generate mathematics. So this is a sample. So basically, this RNN just spits out LaTeX. And then we compile it. And of course, it doesn't work right away. We had to tune it a tiny bit. But basically, the RNN, after we tweaked some of the mistakes that it has made, you can compile it, and you can generate mathematics. And so you'll see that it basically creates all these proofs. It learns to put little squares at the ends of proofs. It creates lemmas, and so on. Sometimes the RNN also tries to create diagrams to varying amounts of success. And my favorite part about this is that on the top left, the proof here is omitted. This RNN was just lazy. But otherwise, this stuff is quite indistinguishable, I would say, from actual algebraic geometry. So let X be a non-zero scheme of X. OK, I'm not sure about that part. But otherwise, the gestalt of this looks very good. So you can throw arbitrary things at it. So I tried to find the hardest arbitrary thing that I could throw at a character level RNN. I decided that source code is actually very difficult. So I took all of Linux source, which is just all the C code. You concatenate it, and you end up with, I think, 700 megabytes of just C code and header files. And then you just throw it into the RNN, and then it can learn to generate code. And so this is generated code from the RNN. And you can see that basically it creates function declarations. It knows about inputs. Syntactically, it makes very few mistakes. It knows about variables and sort of how to use them sometimes. It indents the code. It creates its own bogus comments. Syntactically, it's very rare to find that it would open a bracket and not close it, and so on. This actually is relatively easy for the RNN to learn. And so some of the mistakes that it makes actually is that, for example, it declares some variables that it never ends up using, or it uses some variables that it never declared. And so some of this higher level stuff is still missing. But otherwise, it can do code just fine. It also knows how to recite the GNU GPU license character by character that is learned from data. And it knows that after the GNU GPU license, there are some include files, there are some macros, and then there's some code. So that's basically what it has learned. Good?
Was this done with Minchar RNN, or what was the structure used?
Yeah, so Minchar RNN that just I shown you is very small, just a toy thing to show you what's going on. Then there's a char RNN, which is a more kind of a mature implementation in Torch, which is just Minchar RNN scaled up and runs on GPU. And so you can play with that yourself. And so this in particular was we'll go into this by the end of the lecture. It's a 3-layer LSTM, and so we'll see what that means. It's a more complex kind of form of recurrent neural network. Okay. Just to give you an idea about how this works. So this is from a paper that we played with a lot with this with Justin last year. And we were basically trying to pretend that we're neuroscientists. And we threw a character-level RNN on some test text. And so the RNN is reading this text, this snippet of code. And we're looking at a specific cell in the hidden state of the RNN, and we're coloring the text based on whether or not that cell is excited or not. Okay? So you can see that many of the hidden state neurons are not very interpretable. They kind of fire on and off in kind of weird ways because they have to do, some of them have to do quite low-level character-level stuff, like how often does E come after H and stuff like that. But some of the cells are quite interpretable. So for example, we find cells like a quote detection cell, that this cell just turns on when it sees a quote, and then it stays on until the quote closes. And so this quite reliably keeps track of this, and it just comes out from backpropagation. The RNN just decides that the character-level statistics are different inside and outside of quotes, and this is a useful feature to learn. And so it dedicates some of its hidden state to keeping track of whether or not you're inside a quote. And this goes back to your question, which I wanted to point out here, that this RNN was trained on, I think, a sequence length of 100. But if you measure the length of this quote, it's actually much more than 100. I think it's like 250. And so we worked on, we only backpropagated up to 100. And so that's the only place where this cell can actually learn itself, because it wouldn't be able to spot dependencies that are much longer than that. But I think basically this seems to show that you can train this character-level detection cell as useful on sequences less than 100, and then it generalizes properly to longer sequences. So this cell seems to work for more than 100 steps, even if it was only trained, even if it was only able to spot the dependencies on less than 100. This is another data set here. This is, I think, Leo Tolstoy's War and Peace. This is, in this data set, there's a new line character at at roughly 80 characters in. So after every 80 characters, roughly, there's a new line. And there's a line length tracking cell that we found, where it starts off at 1, and then it slowly decays over time. And you might imagine that a cell like this is actually very useful in predicting that new line character at the end, because this RNN needs to count 80 time steps so that it knows when a new line character is likely to come next. Okay? So there's line tracking cells. We found cells that actually respond only if statements. We found cells that only respond inside quotes and strings. We found cells that get more excited the deeper you nest an expression. And so all kinds of interesting cells that you can actually find inside these RNNs that completely come out just from the backpropagation. And so that's quite magical, I suppose. Go ahead.
How did you figure out what each individual cell got
Yeah, so there's so in this LSTM, I think there were about 2,100 cells, so you just kind of like go through them. So most of them look like this. But I would say roughly 5% of them you spot something interesting, so you just go through it manually.
So you like turn the others off and just leave one on and see what's...
Oh, no, sorry. So we are completely running the entire RNN intact. But we're only looking at a single hidden state the firing of one single cell in the RNN. So we're running the RNN normally, but we're just kind of recording from one cell in the hidden state, if that makes sense.